I wanted to talk basically about two different things, or make 2 points in this talk. So in the first half, I'm going to talk about the price of anarchy, talk about what it is, give you some results for it. The takeaway point of that is going to, or what I hope you take away is that there are interesting application domains in which, game theoretic domains, in which equilibria need not be optimal in any sense. They need not be first best, they need not need to be Pareto optimal, but nonetheless you can prove interesting guarantees, saying that equilibria are in some sense a decent approximation of a first best solution. That's going to be a pretty old work of mine. A few of you have seen me talk about it before, I apologize. And then in part that's an excuse to talk about the second half of the talk, which is very recent work, which I'm very excited about, which is that all of these so-called price of anarchy guarantees everyone's been proving turn out to be much stronger and, in a precise sense, much more robust than any of us realized. And so I want to tell you what the formulation of that kind of statement is as well. Okay, so people have now analyzed equilibria quantitatively and talked about their inefficiency in a lot of different models. I'm going to just tell you about one of the first ones that was ever done, which was back when I was a graduate student. So it's I'm going to give you the model, and there's a lot of letters and stuff, but really this is just cars on the road. Okay, this is just rush hour traffic at steady state and a completely natural mathematical model of how you might think about that. Okay, so that's all this is. Formally, what do we have? We have a network. Okay, so a directed graph with vertices and edges. There's a bunch of traffic that originates in different places. Those are the source vertices, that's S1 through SK. They're going different places in general. So traffic starting from source SI is going to some destination T sub I. Doesn't matter where. I'm going to think about inelastic traffic for simplicity. You can generalize it. Don't worry about it. So a fixed amount of traffic, 1 unit from point A to point B, 2 units from point C to point D, and so on. And now what makes them all interesting is there's congestion. Okay, so drivers or the traffic encounters delay going from the origin to the destination. They traverse a path which has a number of hops. And as everyone knows, when they drive themselves, the amount of time it takes you to get to your destination depends on how many others you share that road with. So the simplest formalism you could propose is you just endow each edge with what I call a cost function, C sub E. So this is something which is non-decreasing. So as it gets more, so it's a function of the amount of traffic on an edge. As there's more, it can only go up. For technical reasons, I want it to be continuous and non-negative as well. Think about this trivial example. You're picking between two highways. Where I work at Stanford, there's two highways called 101 and 280. Which both go to San Francisco. Probably some of you have driven on them. 280 is very circuitous, but it never gets crowded. So that would have a constant cost or constant delay function, always equal to 1. This would mean that it takes you an hour independent of how much traffic X you're sharing that link with. And then the Highway 101 is shorter, but gets congested. So this would say if X units of traffic or an X proportion of the traffic is on the top edge, all of that traffic would take X units of an hour to get to the destination T sub 1. Okay?
Just a quick clarification.
Absolutely.
Can some of the SIs or TIs be the same?
Absolutely. Yeah.
Okay.
Yeah. So in general, there could be as many as n times n minus 1 of those figures.
Yeah.
Exactly.
The cost function is x is what? It's an edge?
X, no. So here, yeah, so if you like, think of a subscript E1 and a subscript E2. It's a little sloppy, so, yeah. Okay, so every edge has a cost function.
And these directed edges?
Absolutely.
Okay.
You can have undirected, that's fine. But directed is more general, it turns out. So think about that. Exactly. Okay, so I just label each edge saying, as a function of how many people you share this with, this is how long it takes you to get from one end of the edge to the other. And absolutely, I hope the talk, I don't think the talk is too packed, so jump in and ask as many questions as you want as I go along. Okay, I definitely don't want to lose you. All right? So that's the payoff structure, the cost structure. Let me tell you about the obvious way to model the outcome space. Then we'll see there's a very simple characterization of what equilibria should be. Then we'll start reasoning about performance guarantees for equilibria in different kinds of networks. Okay. So like cars on a highway or like packets in a communication network, I'm going to be thinking, for the first part of the talk at least, I'm going to be thinking as the players are small. Okay, so there's a continuum of agents, much as in Eric's talk. So that's what we're going to be thinking about. And because we have enough anonymity, I don't really need to think about profiles. I don't really care about what driver number 17, what road they pick. I just want to know the aggregate amounts of who picks what path to drive on. Okay? So that's how I'm going to model the outcomes. They're called flows in operations research, for example. It's just a vector indexed by all the paths going from all the different origins to the different destinations. It just says what proportion of traffic with that origin-destination pair picks that particular path. So here would be one outcome. Perhaps half of the traffic on a zigzag path, half of the traffic on a partially overlapping two-hop path. Okay? So those are the outcomes. nice space of outcomes. And equilibria are very easy to characterize because we're in this non-atomic model, because we have this continuum of players, right? So, and remember, cost functions are continuous, so if one player, one of these tiny players, switches their path, it has no impact on the paths of anybody. Okay, so if you like, players are sort of cost takers in a sense, so it's a very simple game. So I'm going to call a flow an equilibrium. Sometimes they're called Wardrop equilibrium. I might call it a Nash equilibrium, even though it's a non-atomic game. So what does it mean? Why would nobody want to switch? Well, you're a driver going from point A to point B. You see all your options. There's the traffic pattern formed by everybody else. And you want to be on the shortest path. You want to get to your destination as quickly as possible. Yeah, I was just looking at that. That's because I stepped on it. This is actually very easy talk to do on the whiteboard if it comes to that. But, what was the cable problem? Who fixed it?
You should step on it.
And that's enough?
Yeah.
Oh boy. You should have told me that. Pigu's example, this price of energy is exactly 4/3. Okay? So the average cost at equilibrium exceeds that of the first best by exactly 33%. People also talk about the price of anarchy in games that have multiple equilibria. In that case, computer scientists are usually pessimistic, worst-case people. So if you have multiple equilibria, you look at the highest one. Okay, so ideally, you would like a guarantee so that no matter what equilibrium you're at, you know something, you know it's good to approximately optimal. Okay? So here, as I said, there's basically unique equilibrium, so I can just write this and it'll be well defined. All right? Questions about that? Okay. Yeah.
Since you're using, this potential that you defined, what's the do you use in a conservation theory, or it's just something?
You mean where's the potential come from? How do you
Yeah.
prove there's a potential? It's actually, once it occurs to you that it might be true, it's kind of trivial, actually.
Yeah.
So you literally just write down, what does it mean to be in equilibrium? You get some conditions. You say, wow, those look an awful lot like complementary slackness / Cruise-Tucker conditions. I wonder if I can invent a function for which that equilibrium condition arises as the automatic condition. And then you say, oh, well, it's just in terms, basically I want to think of these costs as derivatives, as marginals of something. How do I do that? Oh, I guess I integrate it. And then when I take the derivative, I get the cost back. And so literally the potential is just sum over the edges, integral 0 up to the flow amount of the cost function. Okay, and then you just check. So it's guess and check just works in a couple lines.
So you're taking the potential, you just remind.
Yeah, so I mean, it's just a theorem that equilibria minimize this. That's what they do. Yeah. So another example many of you know, but for probably maybe 50% of you don't know it, this is just a good thing to know. It's called Brace's paradox. Okay. So same story, one unit of traffic going from S to T. They have these two options. There's again ones and X's, although now there's two in series on each of the two paths. And so by symmetry, it's sort of clear what the equilibrium is going to be here. People will naturally load balance. And this is also the first best solution. Right? So it's hard to see why you'd call it a paradox. Right? It just seems very boring. But so it gets paradoxical when you introduce.
Sorry, for the evolutionary biologists in the audience, maybe just what's the best solution?
Optimal. Minimum cost. Minimum cost. Yeah, sorry. Yeah, I'll use that and optimal sort of interchangeably. Yeah. So it becomes paradoxical when you allow people the option of teleporting from V to W. Okay? So that is zero cost independent congestion. So we added a new edge. We clearly made this network better, right? We gave people this extra option just for free. So we introduced a new route, namely the zigzag route, right? And so if you were one of these, if you sort of were listening to the traffic report, if you were a consistent driver and you knew that everybody else load balanced, and then you sort of read the news article that they were introducing the teleportation device the next day, you'd say, well, look, it's taking me an hour and a half to get to T right now. And if I use the teleportation device, right, it's only a half hour. This is for free, and then this is a half hour, so that's an hour. That's going to get me there faster. Okay, I'm going to get there in only an hour if I use the teleportation device. So I'm going to do it. Okay? Of course, everyone reasons exactly the same way. And so if you think about everybody switching, you get everybody on this blue path. Okay? And this actually turns out to be an equilibrium. All right? So nobody would want to deviate from this. In fact, again, it's a dominant strategy. to use the zigzag pattern, right? Because again, this is no worse than 1. Your alternative over here is a 1. Same argument here. Okay, so this is the only equilibrium. Now, what has happened with the teleporter? Well, now, because everyone uses it, this congestion's been doubled. This congestion's been doubled. So the delays along them have been doubled. So everyone gets there in 2 hours instead of an hour and a half. Okay? So that's the paradox. We made the network better. The outcome is worse. This also now shows a strict Pareto domination, right? So what would be the optimal solution in the new network? Well, I would just tell everybody to ignore the teleporter. I just say, go back to the old way. And you'd all be getting there 30 minutes faster. Okay? You could ask also, what's the price of anarchy in the network with the teleportation device? Okay. Well, the equilibrium cost, we said, is 2, and beforehand it used to be 3/2, so there's another 4/3. So that's what's suggested. Cool.
You're exactly there.
Just watch it keep.
All right, so I'm only allowed to roam in this direction, in front of the screen.
Don't move at all.
Don't move at all. That I don't think I can do, actually. So, drink too much coffee. So that's Brace's paradox. Maybe even better, Cohen and Horowitz wrote a Nature paper a couple decades later, where they showed there are analogs of Brace's paradox in certain physical systems. So my favorite is they argued, I mean, and you can verify this experimentally, so you can take a bunch of springs, elastic springs, and a bunch of strings, and you can tie them all together in a contraption, because you've got this jumble of strings and springs. What I'm going to do is I'm going to attach the top of this contraption, say it's something at the bottom of this table, or something higher, think of it, but I attach it to some fixed ceiling, and I hang a weight from the bottom of the contraption, so it stretches everything out. Okay? It exerts force, the strings get stretched out, and so do the springs. Okay? And what is the contraption? Let me just show you the contraption, actually. So here's the top. Okay, so here's the spring. I attach a little mini string here. The podium's going to block this, isn't it? Okay, so this is a spring. A little tiny string. Another spring. And then a big weight. 10 pounds, something like that. Okay, so right now, this is sort of boring and obvious. It just stretches out the springs of weight. All right? Now what I'm going to do is I'm going to attach, with just a tiny bit of slack, a string from the top of this thing to the top of this spring, and from the bottom of this spring on down to the weight. Okay? And now what I do is I take a pair of scissors, and I snip this thing. I cut it. All right? So I've weakened this contraption. It has fewer things holding this weight. And yet, what it does is it disentangles these two different springs, and now instead of the two springs carrying the weight in series, they will carry the weight in parallel. Half the force will be exerted on each, their length will be half as before. And that overpowers the fact that these strings are now in play. So in fact, this weight will levitate off the ground. And under utterly idealized situation, this will levitate exactly 25% of the original height, just as removing the teleporter from this network would remove 25% of the delay. It's exactly the same governing equations, with the correspondence being force in this picture with traffic in this picture. Okay, delays over here corresponds to height here. Okay, so that's Cohen and Horowitz. And also, similarly for a network of diodes and this kind of thing, same kind of stuff. Okay, so that's Brace's paradox. Any questions about that? I'm about to get to some results, but that's the model. And these are the reasons why a lot of people thought about it for a long time.
I can see why it's interesting with traffic, but I still don't understand why you would care about the springs and the weights.
Well, they were physicists, so this was...
What's that?
Well, I mean, one, you can just demonstrate it to somebody.
Okay.
I mean, you can build
Okay.
this. And I have friends who have built it and used it in their classroom.
Okay.
And I think if you're kind of a physicist mind, then this is it's a very cool demonstration. It's less abstract. Yeah.
What are you talking about, Steve? That's exciting.
But to each their own. So, if you find at least one interpretation interesting, then I'm totally happy with that. So. Okay, right. So what's the goal of this first half? So the goal is to understand under what conditions, for which networks, can you prove a meaningful guarantee of the quality of equilibria. The price of anarchy gives us a metric to make precise sort of goal, like equilibria are usually pretty good. Maybe they're not Pareto optimal. They can be Pareto dominated, but they're still pretty good in some sense. The closer the price of anarchy is to 1, we interpret that as more and more benign and selfish behavior. Okay, if price of anarchy is really large, it says you've got a real problem with your network, change the network, introduce a mechanism, introduce a price system, do something. But if this is close to 1, maybe you don't have to do anything at all. Maybe you can just leave it be and you're pretty happy with the performance. Okay, so that's the goal, theorems of that form. Now we have 2 examples. I've only shown you 2 examples, and the price of anarchy is pretty close to 1 already, right? 4/3, 33% loss. If we're doing nothing, it's not so bad. But it's not always so good, okay? So I can modify Pigou's example in a very minor way. I can take what used to be a linear function x on top and make it highly nonlinear. Okay, so look at this as 10 or 20 or even more, all right? So the equilibrium flow is invariant. It's independent of D. So the top link remains a dominant strategy no matter what D is. So all the equilibrium flow will use it, and the average cost will remain 1. But in the optimal solution, you can really make use of the fact that this is now very steep and very close to 0, close to 1. Okay, so if I start from equilibrium and I take an epsilon fraction of this traffic and I make them martyrs by rerouting them on the bottom one, sacrificing them to the bottom one. Remember, I'm looking at the average cost. Okay, so almost everybody 1 minus epsilon of the traffic has almost 0 delay, 1 minus epsilon raised to the d. Okay, so if you set d sufficiently large and epsilon's in the right range, this is almost nothing. This epsilon contributes almost nothing to the average. So we get optimal cost going to 0 with d. We get the ratio of the equilibrium and optimum cost going to infinity with d. Okay, a little bit sublinearly in d, roughly linearly in d. Okay, so in other words, there's no way to prove a theorem like for every quote-unquote selfish routing network ever, the price of anarchy is at most 4/3. This shows that's just utterly false, even if you look at the most simplest networks you could possibly imagine. Just a binary decision for everybody. Okay? So that's the kind of theorem we can't prove. What are the kinds of theorems we can prove? Well, so the other thing to do is think about restricting the cost functions. So let me give you an example. I'm going to give you a much more general theorem in a couple slides, but to warm up, let me show you the first one that was proven, which is for totally unrestricted networks. The network can be as big as you want, any traffic matrix doesn't matter, but let's look at linear cost functions, ax plus b. A and b can be different for different edges. Okay, so obviously these were linear cases. So this is a modest generalization. So the cost functions are a modest generalization. The network is a massive generalization. I'm saying any graph at all, okay, and any number of origins and destinations and so on. Then the 2 examples I've shown you are the worst, turns out. Okay, so 33% relative loss is the largest you will ever see in any network for any traffic matrix if all of the cost functions are linear, or affine, if you prefer. Okay, so that's the theorem. All right. Make sense, the theorem? Okay. So we know that this number, so what I want to do next is move toward a generalization. And we even need to think about what would be the reasonable, what would be the right generalization of this result. I've already convinced you that this 4/3 is certainly an artifact of this assumption, right? The nonlinear version of Pigou's example demonstrates that. So, but maybe there's some analog of this theorem nonetheless, which will be independent of the linearity assumption, which would be a suitable generalization. And there is. To motivate it, let's look at a corollary, a sort of obvious corollary at this point of this result, which is that we definitely know that 4/3 cannot be replaced by any smaller number, even with this assumption. We know it from Price's paradox, but we also know it from Pigou. And this is what I'm more interested in, okay? So Pigou's example, the original one, the one in the X, meets from below this upper bound of 4/3, okay? So we already know this. So, and this is kind of remarkable, right? Because it gives us a sort of structural characterization of worst possible efficiency loss in a huge infinite class of games. Okay, remember what we're looking at. We're looking at all networks in the world, and we can get very complex. Any traffic matrix, linear functions. I say, conceptually search over all of them and show me the worst efficiency loss you'll ever see. And it's kind of a dirt simple explanation. Well, look, the worst thing that ever happens, the most severe type of efficiency loss is just selfish users' inability to detect a very simple congestion externality. Unable to detect that when they use this more than 1/2 of these 2 different routes, actually they're making everybody else worse as well. Okay, and that's the only thing that's going on in Pigou's example, and that dominates everything else that happens. Every other. So, I mean, just to give a straw man argument, the other thing that I was worried might be going wrong, the reason I thought maybe you'd see bigger numbers in bigger networks, you can imagine you have some maybe very tricky traffic matrix where everybody's on the periphery, lots of sources, and somehow in the equilibrium everybody dives into the core of the network, and there's tons of congestion and everything's really slow in the middle, and it takes a long time for them to merge to the other side and get to their destinations. Whereas the optimum can somehow cleverly coordinate around the periphery. Before this theorem was proven, I thought that might totally happen. That in bigger networks, you might have bigger inefficiency. This says it's not true. And the main reason I mention this is the proper generalization of that 4/3 result to the nonlinear case. Okay, the 4/3 is an artifact of linearity. The fact that a dirt simple network achieves the worst case bound is not an artifact of linearity.
Is the price of energy, that's defined on the network itself, but it's not defined on, say, like subsets of the network, right? I mean, say we take this example you have up here, but instead of everyone starting at that point S, you move them up, you add a link, add an edge between what you currently have S and say something that's just a little to the left called S, that everyone has to take.
Okay.
Obviously, you're going to drive down the price of anarchy.
Yep.
So, but you're not really interested in that other edge because there's no choice involved there, right?
Sure.
And so the only part where you really be concerned about the efficiency, but it would look, but say that the cost was 1,000 there, that one.
Right, so that would be not a very interesting example, basically.
Well,
so if everyone's stuck with very huge cost, then if you care about sort of relative differences, then different epsilons is not a big
So that's
deal.
why I was wondering if this price of anarchy idea is only something that you'd want to apply to the part of, so if you don't want to take, so when you said that, you just make the network bigger, your price of anarchy has this upper bound.
It does not get worse, right?
Right, so I'm wondering if that's not exactly the right way to think about it. It's not making the network bigger itself, it's only making the network bigger in particular ways that are really going to add to the price of the anarchy.
But even particular ways don't do it, is what's remarkable. So for example, if you look at a different objective, if you look at a kind of more egalitarian objective, where you want to minimize the worst case cost, this is no longer true. I mean, so then you really do get linear growth in the price of anarchy with the network size, even for fixed cost functions. So this is not sort of an automatic property of these kinds of network type problems. It's really, I don't want to say lucky, but it's kind of a very, it's a very nice property, which is not always satisfying. Yeah. So.
Is that true also if you look at non-atomic games?
Yes, right. So this also breaks down for atomic games. So one of the things that is a corollary of the new results I'll talk about, but I won't actually state it, is you can. So for the first time, there's now an analog of this theorem, which characterizes what the worst case networks are in the atomic case. So they're more complicated. It's no longer just two parallel nodes. It turns out you need two parallel cycles with appropriate connections between them. So you can get a characterization, but it's not as simple. Yeah. Okay.
I think Eric had a question.
Oh, sorry.
Oh,
Yeah.
no, it's okay. You showed that your price of anarchy went up when the cost function became more. Well, you showed two cases, very concave and not concave at all.
Right.
Can you show any sort of monotonicity? That is, that the price of anarchy rises as the concavity of the cost function increases?
Yeah, to some extent. So the extent to which I can do that is going to be this theorem. And there's certainly sufficient conditions, like if it's a polynomial, you're going to have monotonicity in a degree. If it's some other kind of naturally parameterized function, this will give you as a consequence, I'll explain in a second, this will give you as a consequence monotonicity in that parameter. In general, I'm going to be thinking about all cost functions in the world, including weird step-like functions, in which case it's not actually clear what, you have to define more convex. But so this is the most, at that level of generality, this is the best I can do. But for natural parameterized families, you get exactly that monotonicity. So what is it?
One question, when you reduce it to this two-node, two-link network, does it reduce to linear cost functions in the two-node? I mean, you start out with general cost.
Let me explain this, yeah.
Okay.
I haven't even stated the theorem yet. I know it's been on the slide for a few minutes, but let me explain it. So what did we prove under the linearity assumption? We proved, one, the price of anarchy is the most 4/3. As a consequence, Pigler's example achieves that upper bound. Okay, and I said 4/3 depends on linearity. A sort of trivial matching lower bound does not depend on linearity. So here's what I really mean. So here's the most general version of the theorem I can imagine, which says fix any restricted class of cost functions you want. I don't care what. Quadratic, cubic, Q and delay function, finite set of 23 functions, I don't care. Okay, just tell me what cost functions I'm allowed to use in my networks. Then, on the one hand, and now conceptually do the experiment is, okay, among all of these trivial kind of networks, formally what I mean is I restrict you to a source, an origin, two parallel links. One of them has a cost function, a constant cost function, excuse me, like that one. Pick whatever nastiest cost function you want for the other link, okay? That is the power I give you when you're searching for a worst case example. I give you 1 degree of freedom. Pick the cost function for that second link. I stick you with a trivial two-node two-link network. I only let you pick, and I stick you with a constant cost on one link. You pick anything else for the other link. The theorem says the number you will get from that optimization, trying to find the worst example, the highest number, the highest price of anarchy, is exactly the same number you will get if you maximize over all networks in the world, all traffic patterns, and with that have cost functions from the same set. Okay, so we're looking at two different suprema, one over a superset, one over a subset. The superset is what we really care about. We just want to know what's the worst network ever, no matter how big, no matter what the traffic is, with these cost functions. The subset is just these trivial examples with two nodes, two links, and a single constant cost. And the claim is those two suprema are equal, no matter what the cost function is. Right? So in the linear case, you will get 4/3 from both these suprema. Right? The worst case over all networks in the world is 4/3. The worst case over all of these trivial networks is also 4/3. That we know. Here, the claim is that equality will always be true. You'll get different numbers. For the quadratic case, you'll get 1.6. For the cubic case, you'll get 1.8, and so on. But you will always get the same number, maximizing over all networks or maximizing over trivial networks. So trivial networks are universal bad examples for the worst case price of anarchy in substrata networks. That's the theorem. Does that make sense?
Why?
Why? Good question, right. So a natural way you might think about proving this, especially if you like taking some graph theory, is to try and sort of take a big network and then do some kind of reduction operation. Do surgery, take two nodes and fuse them and do this kind of thing. I actually do not know a proof that works that way. There might well be one. There's about 6 proofs of this theorem by now. There might be a 7th along those lines. Six proofs of this theorem or something. I mean, they're not. Some of them are not super different than each other. There's one, actually. There's one. I mean, if you want, I'm not going to have time to do it here, but in the break, I'm happy to talk about this. So the cows come home. There's one which that Eva Tardos came up with, which has it's both the longest. So I rarely put it in talks, but it also has the most combinatorial flavor, and it gives you the strongest combinatorial intuition of where this comes from. You sort of take a network and you add a bunch of links, and then sort of decompose it into a kind of direct sum of parallel networks and do an averaging argument. That is not how the short proofs work.
But what about the economic intuition? The inefficiency comes about because of the externality.
Right.
In a two-node, two-link network, in effect, you are maximizing the amount of externality you're going to have because everybody has to go on.
Possibly. I think especially if you think about everyone having the same origin and the same destination, that's a very powerful intuition. And in some ways, when it first occurred to me, that's sort of how I thought about it. I was sort of thinking one origin, one destination. Think of that being like a sequence of cuts that you're passing over, and then you sort of, the equilibrium has more on one part of the cut and less on one part of the cut, and that's really just this kind of two-node, two-link thing. But it gets a little harder to just hand wave through once you have all the traffic crisscrossing each other, I think, and maybe piling on top. There, at least personally, I find that economic intuition less convincing. I don't. You may still find it convincing, but with lots of people crisscrossing each other, I'm less. I mean, it's true. So, okay. So as far as I was only going to say one line about why this is true, which is, in a large extent, this boils down to the potential function. Okay. And in fact, if you want to prove slightly weaker versions of this, you can get a very easy 3-line proof using the potential function. What's the idea? So again, remember, equilibria can be characterized as optimizing this potential function. Now, one thing we know for sure is what they're optimizing is wrong. If what they were optimizing was what we really cared about, average cost, the price of anarchy would always be 1, and it's not. So whatever they're optimizing is, it's wrong. But it looks pretty reasonable, right? It's a sum over the edges of some kind of average edge cost over this interval. And if you had, say, linear cost functions, basically, in the objective function we really care about, you're going to get an ax plus b. In the potential function, you're going to get a 1/2 ax plus b. So in other words, the potential function will be a point-wise 2 approximation of what we really care about. So equilibria are optimizing a function, which is wrong, but wrong by only a factor 2, and therefore, with respect to the objective, they're going to be optimizing a factor of 2. That does not give you the type down, that does not give you the 4/3, but it kind of shows you how to get started. So you can basically build on this, do something a little slicker with variation of the qualities and get the type bounds. Again, it's not a long proof, so in the break I'm happy to show it to anybody who's interested. Okay? Other questions about that?
Does it carry over to the physics exam?
Say it again?
Does it carry over to the physics exam?
Doesn't carry, absolutely. So it also says that no matter what strings and springs you put together, snip whatever you want, the biggest levitation you'll ever get is 25% of the original height. Absolutely. Other applications I like, so like I said, this is an old model and people have thought about it in a lot of contexts. Some transportation books, if you open them up, they'll say the quartic functions are a good cost function to use for road traffic. That's controversial, but there are definitely camps that believe that. And then you just figure out what the worst case example is. It's just the 1 and x to the 4th example. You go back at the envelope calculation, and this general theorem tells you it gives you an upper bound of 2 for all networks. That you derive the number from the 2-node 2-link network. That's where you do the calculation. But the theorem promises you that the upper bound is valid for every road network, any traffic pattern. Similarly, communication networks, people have used this model a lot ever since the 70s. There, people often think about MM1 delay type queuing functions. So where you have sort of an asymptote where things get very steep near the asymptote. So there, because it's so steep, the price of energy can be unbounded. But if you talk to anyone who actually runs an actual communication network, if you talk to an internet service provider, they'll tell you that they over-provision their networks. Part of that, of course, is to anticipate future growth and demand, but part of it is to make performance optimization intuitively much easier. So they'll just tell you empirically, with extra capacity, the networks just function far better in a lot of regimes, and this sort of gives a rigorous backing for that. So if you have, if you look at MM1 delay functions and you formalize the idea of having, say, 10% extra capacity, so 10% more capacity than you need just to support the amount of traffic, then in fact that drives you away from the asymptote down to something like a low-degree polynomial. And again, you get the price of energy is basically around 2 for networks that are a little bit over-provisioned. Okay, so those are some easy consequences from the general theorem, which I like. Yeah.
Here you're forced to take the trip, right?
Right. So this is inelastic. Yeah.
Exactly.
So
this results if you could choose. I mean, if you have a value to going to. If you have a value to going to the sink, and then you could make a choice of not even stopping.
There are versions of it. There are versions of it for elastic traffic. Roughly speaking, so if you model it as having an opportunity cost in some sense, that's kind of like as if I have an artificial extra path from a source to a sink, which I label with that person's sort of lost value from the trip. So on that sort of superficial level, they carry over. If you start subtracting things, if you start having values minus costs, then you start exposing the kind of technical problems with the ratio, and you start getting sort of imbalances. But if you think about opportunity costs, everything works with no changes, actually. Okay, so I don't want to totally skip the second half, so let me move on to it. I do want to say a little bit about the new results. The thing which by design is nice about a price of energy guarantee, and again, remember, in models with multiple equilibria, which I'm going to talk about now very briefly, what you do is you look at an upper bound on the worst equilibria, and you prove a bound on this ratio. Okay, and like I said, there's many, many other models. People, largely in computer science, have been bounding these ratios and proving them close to 1 under different kinds of assumptions. So what's nice is, so if you have a small constant upper bound on the price of energy, it says, as long as players get to an equilibrium, you do not care which one, you are guaranteed good steady state performance. Right? That's the interpretation. And so the new theorem I want to show you is meant to rebut the critique as well, and this is now getting closer to the adaptive systems spirit of this workshop, which is, why do we think people are at equilibrium anyways, at all, anything, right? Certainly we see systems all the time which are not at equilibrium, which are clearly always seem to be searching for an equilibrium and oscillating along some trajectory, okay? So sometimes you can sort of posit dynamics and prove convergence to equilibria, then obviously the price of energy bounds kick in because you're at an equilibrium. What I want to do is I want to extend these kinds of equilibrium results to hold for stuff which is not even in equilibrium. So for much bigger sets of outcomes or trajectories of outcomes, not just Nash equilibrium. Okay? Now, of course you have to assume something, right? So you could always have a strategy in your game where somebody just sort of shoots themselves. And if everyone picks that strategy, that gives you an outcome where there's not going to be any balance. So I need to assume something. So what could I assume is weaker than Nash equilibria? So there's a bunch of things. In the interest of time, let me just mention one. Okay, so there's a bunch of different equilibria, each of which generalizes the previous one. let me focus on something which is even more general than mixed or correlated equilibria say, which is sequences, and I'll define this formally in a few slides. But for now, the point is I'm looking at experimentation by players over time. So I'm no longer looking at a single outcome. I'm looking at a sequence of outcomes where each one is generated from the previous one by some kind of synchronous or asynchronous experimentation by the players. Okay? So best response dynamics might be more familiar to many of you. This is kind of a sort of greedy search for a pure Nash equilibrium, because everyone picks a strategy. If somebody's unhappy, an arbitrary such person does the best response and tries to get better. And if this ever converges, it'll be a pure Nash. No regret is more of a search for something else, a mixed or correlated equilibria. And again, just think of it, I'll define it for you in a second. Think of this as people not even knowing what game they're playing. They don't know who their opponents are. They don't know what other opponents' payoffs are. But they at least see their own payoffs. And using that, they do some kind of suitable hedging to make sure they do reasonably well over a trajectory. Okay? And if you look at sort of the empirical distribution over outcomes, you can get any correlated equilibrium, you can get any mixed equilibrium, but you also get other stuff beyond correlated equilibrium. So again, the takeaway point, if you haven't seen these definitions, is just there are subsets of outcomes, which are not everything, which have some kind of game theoretic justification, but which are much weaker than thinking about Nash equilibria. And these are the kinds of sets I want to prove in more general sense. Yeah, good point. Yeah, okay. That's a good point.
So what kind of games are we talking about?
Think about selfish routing right now.
Potential games.
For example.
So when you say that the best response dynamics, are you thinking about the limit points of that dynamic?
So this is a good point. So what do I really mean? So because when I say a sequence of outcomes, if the sequence has a length 1 and I have a bad start state, again, I'm not going to be able to prove anything. So what I mean in a sequence is I mean for a sufficiently long sequence, but not too long, polynomial. So here I'm going to stop it. So to answer your question, I'm going to stop best response dynamics before it gets to pure equilibrium. 5 minutes. Okay. So I'm going to run this for like a linear number of steps.
I see.
It won't be a pure.
Then I didn't understand why you're actually having as a subset pure Nash. Because
Fair enough. Yeah. So think of this as best response dynamics after I terminate it when I get bored with it, and I still want to be good. Okay. All right. So here's the informal theorem. Okay. So basically, what it says is bounds on the price of anarchy, which historically have been only about pure equilibria. At least the way we've been proving bounds on the price of anarchy, and I'll make this more precise in the next slide, actually automatically extend to all of those bigger sets. Okay? So in particular, like this 4/3 that we proved, the analog of the 4/3 in atomic routing games is 5/2. The original proofs are only for pure equilibria. The claim is bounds like that not only are for pure equilibria, but they also for mixed, correlated, and empirical play of these sequences. And in fact, any proof, any upper bound on the price of anarchy that has a certain form, with no additional work, automatically implies this much more general statement about these much bigger sets of outcomes. Okay? Right? Any guarantee is more compelling the bigger the set of outcomes it applies to. And this says, pretty much the only way we've been bounding the price of anarchy automatically extends to these much bigger sets. It's automatically a much more robust guarantee than we previously knew. Okay? All right, so I do want to at least tell you what the definition is. Okay? And so to tell you the definition, this is one of those theorems which just gets pretty easy to understand if you zoom out to a suitable level of abstraction. So in your mind, think about a selfish routing game. Think about players picking paths with costs. But let me just give you the completely abstract setup. Finite number of players, each picks a strategy. For a vector of strategies, an outcome S, everybody has a cost. The theorem is only about some objectives, okay? Like in the selfish routing examples. So our price of anarchy results are going to be about the sum of the player costs. And now I want to ask, at this level of abstraction, how would we ever prove an upper bound on the price of anarchy? What would it look like if I told you nothing else about the problem domain? Okay? So look at a Nash equilibrium that we want to prove has low cost relative to an optimal solution S star. Well, we have like no hypotheses. So, I mean, our proof, this is as far as we can go with our proof, and this is sort of the unique thing we can do with our hypotheses. This is what we want to upper bound, the cost of an equilibrium. All we know is that the objective function looks like this, and the only other thing we know is that S is a Nash equilibrium. In particular, if we made a player switch to what we wish it was doing in the optimal solution, the cost would only go up. Okay? So just from the form of the objective and the assumption that it's a Nash equilibrium, this is our proof. And now, suppose we can write down the next line. And depending on the exact problem domain, depending on the application, we may or may not be able to write down a line like this. So it's parameterized by lambda and mu. Lambda is positive, mu is less than 1. Suppose we can disentangle this cross term that simultaneously involves equilibrium and optimal outcome strategies. And we can charge this, we can upper bound this by a lambda factor times the optimal cost and a mu factor times the equilibrium cost. We may or may not be able to do that. If we can do that, then evidently we have proven that every pure Nash equilibrium has price of anarchy equals lambda over 1 minus mu. Right? We just move this over to the left-hand side and divide through. So this is a kind of content-free upper bound on the cost of a Nash equilibrium. Okay? So the key definition, and I'm almost done. So I call a game smooth with parameters lambda and mu if star holds. Okay, not quite star, something that seems only a little bit stronger than star, but is incredibly crucial. Okay? So what does star say? It says if S is an equilibrium and S star is an optimal solution, then I can write down this inequality. Smoothness says if S is any outcome, not necessarily an equilibrium, and S star is any outcome, not necessarily an optimum solution, then I can write down exactly the same inequality. In other words, given any two outcomes entangled in this way, I can disentangle them with these loss parameters lambda and mu. Okay? This now is my definition of a canonical way of proving an upper bound on the price of anarchy of a game. Okay? You write down this line, you write down this line, you work really hard, and you use problem-specific information about that game to prove that this inequality holds for every outcome S and S star. What I've shown you from this derivation is that then you know the pure price of anarchy is at most lambda over 1 minus mu. Right? That's what this derivation shows. But because I've proven it for every pair of outcomes, S and S star, it turns out lambda over 1 minus mu is going to bound the expected payoff in everything in all of those 5 sets. Okay? In other words, smoothness is a sufficient condition for an upper bound on the pure price of anarchy. And if the way you derived an upper bound was via this sufficient condition, you get all those other 4 sets for free. Okay? So that's the formalization. Now this would be useless if you couldn't actually ever figure out games that were smooth. So when I first came up with the idea of this definition, right, definitions are cheap. Any schmuck can come up with a definition. You got to show that they're useful. So I was like, well, you could do this definition, but is it good for anything? So I started randomly sampling both my work and other people's work, and I said, you know, are people using smoothness arguments? And actually, every analysis I could find was either a smoothness argument, or I could reformulate it so that it was a smoothness argument. Okay, so every price of anarchy analysis in the literature that was a sum objective, this theorem actually applied to. And it automatically extended to all 5 of these sets. And it turns out there's actually something fundamental about that. And I'll leave you with this. You can actually prove that as long as your class of games is sort of sufficiently rich, so if you're thinking about a class of games which is infinite, has enough structure, for example, selfish routing networks with some cost functions, you can actually make a mathematical statement that says optimal bounds on the price of anarchy have to be smoothness results. Okay? So you can prove that for a rich class of games, if you optimize over lambda and mu, the upper bound that results will be correct. Okay? So it is not an accident that the 4/3 for non-atomic selfish routing arises from a smoothness argument. It is not an accident that the optimal type bound 5 pass for the atomic case arises from a smoothness argument. In every class of games, you can prove that this sufficient condition is actually also necessary. Okay? You get a tight, you get no gap between what you can prove with a smoothness argument and what is actually the ground truth, what is actually the right worst case. Okay? So I'm over time. Let me stop there. Thanks.
Would this extend to the price competition games?
I have to look. Did you use the smoothness argument? No. No? Okay. I have to remember exactly. You have to remind me the definition.
It's a big issue. I mean, to extend from pure Nash to mixed Nash, pure price equilibrium.
Is it some objective?
I think it would be interesting if
okay.
it extends it to that case.
But do you have an interesting class of games where smoothness will not work?
So the sum objective is crucial. So if you don't have a sum objective, so in general, you're going to have, this will be the picture. If you just fix, say, a single game, and you don't look at a class, then in general, in correspondence with those bigger and bigger sets, you can have an optimal solution, and then the worst member of each of those bigger and bigger sets will start going along the line, and then your smoothness bound will be way out here. Right? So this is the general picture for kind of any game, basically. And so certainly for a fixed game, you'll have gaps. And definitely you have strict gaps, and smoothness is wrong if you say, look at, so if you wanted to say, minimize the worst case cost of any player, which you want to do in some kind of load balancing contexts. So basically if you're sort of assigning tasks, and you basically want you want the most loaded person you want it to be load balanced. That's naturally a kind of min-max objective. And this fails badly. There are lots of counterexamples out there. So what would be more interesting, and I'm sure there are games, but again, the first 6 I looked at were not counterexamples or positive statements, would be a sum objective where you have a gap between the best possible and the new choice and all this other stuff. Azu's maybe suggesting one right now.
Yeah. So if you have multi-stage games, you will not have the sum of the costs.
Okay, yeah. So that's the really, I mean, so I claim nothing if you don't have a sum objective. I'm not claiming anything. So, but some objective games seem unbelievably well behaved, and this kind of explains why. That said, I mean, there is, Theorem 2, I mean, so I give sufficient conditions for there to be no gap, but I have not characterized that. I would love to have that, basically, roughly a characterization on classes of games for which you have no gap. But I think the metaphor to keep in mind here, it's sort of like a, when is there no duality gap? Or when is there kind of, I mean, this is not mathematical, just metaphorically. There's a sense in which, any smoothness bound is an upper bound on kind of all of these equilibria, and you can generate lower bounds by exhibiting games with bad equilibria, and the question is when do they match and when do they not? And you'd like to characterize that, but I think that's a little bit like trying to say, can you, characterize linear programs that have integer vertices? So I think the best we can hope for is kind of, widely applicable sufficient conditions, and this is sort of a start, but I'm sure there'll be more. So, yeah.
I mean, is it possible that the set of solutions are actually coinciding?
So what this kind of says is that
games, I mean, that this is not.
So the way to interpret Theorem 2 is in worst case examples, all of these sets are coinciding. It is definitely not true that in a sort of, if you pick an arbitrary game from this class, you will have gaps between all of these things. So you cannot prove pointwise for every single selfish routing network, all of these things are the same. That's just false.
For example, I guess in supermodular games, we know that even though the sets are different, the bounds
That's right.
coincide across these solutions.
That's true. No.
So the question is whether.
Yeah, no, things are definitely more complicated. So say for the selfish routing games, things are much more complicated. So you can actually have, so in a general case, you might have a huge gap, say, between mixed and correlated. So there are known examples where you have massive gaps between the worst case mixed. The worst case mixed would be very close to optimum, and the worst case correlated would be very close to the smoothness bound. But if you look at sort of worst case examples, all of them are going to be all the way to the right.
And all of them are going to be this short game in some sense.
So this theorem is actually much more general. So for the second half of the talk, theorems 1 and 2, this is really not about selfish routing. So the only hypothesis about this is that it's smooth. And there are many examples of games which are not selfish routing games but are smooth. So there's maximization games, there's facility location games. A lot of it is congestion games, but there's some other stuff for which it's not true that trivial networks are the worst. And yet the smoothness will still give you optimal results. So this is more general than the first main theorem that I mentioned.